All right, let's see. Is the audio working? Beautiful. All right, let's move the camera. Nope. Let's make sure the focus is good. Come on, you can do the thing. All right. All right, and we are back. So last time I talked about integrals as inverses, as just the reverse of different differentiation derivatives, and that is true. So, but there's a second way to look at integrals that's also honestly just as important conceptually, but also we then connect to doing the or doing the inverse, uh, the reverse of taking a derivative. So it's still connected to it. The point is that there are two different ways of looking at the same thing. An integral is the reverse of taking a derivative. But there's another huge thing that integrals do for us that you don't get out of just thinking of it as the reverse of a derivative. So what I want to do is I'm going to set up. Okay, so I'm going to set up a graph, and I'm just going to tell you what we're going to talk about with the graph. But I'm going to set up a graph. So give me a second to do that. Um, all right. Uh, function. Yeah, I think it's that. Yeah, I believe it's that. Mm. Where did I just put that? There we go. Function number function 3 over x squared minus. Let me get a little bit of a graph there going. Nice little vertical asymptote at 0. So let's do 3, 6, something like that. And plug in a 1. Actually, I may need more. So 2, there's gonna. Maybe do 1, 2, 3. All right. So if I plug in a 1, that gives me a 2. Plug in a 2, that's 3/4. Minus 1. So that means, actually, give me a second. Sorry, guys. Let me slightly alter this. So it's just works a little cleaner for this example. Well, let's do something like maybe, yeah, let's do +1 instead of -1. So that'll actually then be 3, and then 3/4 plus 1, so 1 3/4. Something like that. So 1/3 plus 1. That. Or, yeah, so we're gonna keep getting closer and closer, and when we have an idea, or at least hopefully, you already kind of saw that or remember well from all algebra that this should have a horizontal asymptote at one. So, 1/3, a little closer still. So the graph of this is roughly like this. Just keeps skating along there and keeps going up towards there. I'm gonna erase this now for this horizontal asymptote there for now, though, just because we need to see some other things in that space. So a bit, I mentioned to you guys at the end of the last lecture, sometimes the last lecture, but especially at the end, that there's a classic problem that literally, not just mathematicians, but carpenters, architects, whatever, building designers and makers have been trying to figure out for a long time in world history, which is if I wanted to find the area under this curve from say, let's say I wanted to go from like one, so I'm basically gonna block it off here to, I don't know, let's do to 5. So if I wanted this area, how would I find that? And Euclid, in putting together his volumes on geometry, did a ton for us as far as finding area for a crapload of different polygons, and then you can combine those together and make weird shapes out of that and still find the area on those things. However, even a curve as simple as this doesn't obey any of the equations that we have from Euclid. And you can't even get it as a combination of some of those equations, right? So the problem historically, literally for thousands of years, whether it was after Euclid or before Euclid, because again, remember that the cultures before Euclid had a lot of the knowledge, or at least a lot of the ideas, and even some of the equations that Euclid later put together. He was the first one that we know of that really rigorously not only put it all together, but rigorously proved it all together, right? So that was really his huge accomplishment. It's like 13 volumes, I think it is. That is 13 huge books of a ton of mathematical knowledge. That some of it that he figured out, some of it that Egyptians, Persians, Chinese civilizations had figured out sort of before him. But they figured out like one fact, right? So they figured out this thing or that thing or this thing or that thing. He was the first one. Euclid was the first one to kind of put it all together and prove that it all exists within the same biosphere, to prove that from a couple basic assumptions, you can prove all these different facts that either, again, we had accumulated or we didn't even know up to that point. So what he did was freaking huge, quite literally 13 volumes. And it really made it so that all of these formulas and all these things we understand about area and volume, lines and etc., are a whole logical universe of facts that not only work well consistently within each other, but then we can use to figure out other things, right? So he did that, but even after that, the problem was something as simple as this, or maybe even a cubic function, right? X cubed, or some polynomial based off of x cubed. To find the area under here ended up being kind of impossible, actually. All of those formulas, none of them even combined together or transmuted together could really get you an exact area for this. And so people have been working on it literally for thousands of years. So Newton and Leibniz, when they invented calculus, were the first ones basically to solve it. So again, in a Cal 1 class that you've had before this, hopefully again, the teacher really emphasized the really big thing that is done first half of calculus, and you talk about the derivative all the time, is we figured out the slope of a curve at any point on the curve. We figured out the slope of the tangent line. That was again another thing that you couldn't actually do with Euclid's geometry, because you at least needed 2 points to find a slope. For thousands of years, they were trying to figure out another way to figure out the slope of that tangent line right at, the point on a curve. And they couldn't do it until Newton-Leibniz. And the second thing, so just again, pause to think about how freaking huge that is. Like that, again, so you guys will see as you go through, and I'm sure you're already seeing as you go through your science and engineering classes, the derivative and the integral are kind of the key for doing a lot of our modern day, honestly, engineering analysis, etc. So in some sense, it's like the world was waiting for these things to be figured out. And I say the world kind of loosely, but I'm saying like sort of prophetically into the future for things to move on, sort of move past a certain point civilization wise. Like the world was just waiting for that. And these guys figured it out. And then the world was also waiting for how can I figure out the exact area under this curve. Because so like the derivative, like I'm saying, that's the slope of the tangent line at a point. Again, this was one of those things that going back thousands of years, you can draw a line there. We know there's a slope. The trick is figuring out what that slope is. So it wasn't some like discovery of something crazy new. It was like, no, we know this is it. We know it's here. We just can't figure out how to get it, right? So the same thing with this. I mean, I make this into a mold, I pour some, plastic or some paint or whatever, I pour something there. I know that there's an area, but the freaking crazy thing for thousands of years is we couldn't actually calculate that area, couldn't get it exact. So again, Newton and Leibniz figured out exactly how to get this area. And that is the two huge things. I would say also the idea of a limiting process having a limit. So they proved that a limiting process has a limit, which is huge. That had been speculated before. The Greeks used it in a ton of, they tried to use it in a ton of mathematics, but they couldn't prove that it definitely was there, right? So Newton and Leibniz proved that it was there. There was a limit, and because of that, they then could figure out the slope at a point on the curve and the area under a curve. And like I said, honestly, that's what allows us to do a shitload of modern engineering and science analysis. So, anyways, okay, so I'm saying they figured it out, but how do we do that? What did they figure out? So I'm gonna start by actually. So we're gonna look at this little area. It's bounded by this line x equals 1 and x equals 5. That's just giving you guys some of the vocab, the terms that they're going to use to describe what's going on here. So it's bounded by those, and it's bounded by the actual function 3 over x squared plus. But we want to find the area right in here. So let's start with how would we solve this? Again, we don't know how to solve this problem yet, right? So let's do what people did for thousands of years. Let's look at how they tried to analyze this problem and then kind of what we do to get the answer. So the way you try to analyze this problem, so you want to figure out the area under this curve. So what we did for thousands of years, or what's pretty obvious, is that what I can do is I can draw, right? So I can draw up the side here, and at this point where we're starting, I could make a little rectangle coming over, and right now let's make the width of this rectangle 1, right? And so I can calculate this area of this rectangle. Now the area of that rectangle is obviously bigger than the area that's actually under the curve, which is a problem. But again, this is sort of where people started. It wasn't that they understood it was bigger, but they're trying to at least approximate this area, right? So we could draw a rectangle from 1 to 2, and then we could draw a rectangle from 2 to 3, again, using whatever the function's value is at x equals 2. Then we could draw a rectangle from 3 to 4. And we could draw a rectangle from 4 to 5. And we could calculate the area of these rectangles. And that would give us an overestimate, but nonetheless, it would give us sort of an approximation, something that's close to the area, definitely over it, but at least maybe close to it, right?
So let's look at how, really quick, let's look at how you do each of these calculations. So I'm finding the area of a rectangle, right? So I just need width times height. Now for each of these rectangles, then the height is gonna be point on the curve, so it's gonna be f of whatever the x value is there, right? So the way that we're calculating this, we kind of have, so what I'm gonna do is I'm gonna say this. Well, so the x values that I'm kind of using here at the left ends of these rectangles is a 1 here. So for this first rectangle, I'm using 1 as my x value. So what I'm going to do is I'm going to take f of 1 and I'm going to multiply it by the distance here, which is in this case 1. So for the distance they call delta x. And to start off with, the distance is 1. So this calculation right here, f of 1, whatever f of 1 is, times delta x, which is 1, that'll give you the area of that first. Does that make sense for everybody? So then what I would be doing is I'd be adding the second rectangle. So the second rectangle, the height of that rectangle is f of 2. Good. And then the width is still delta x. X equals 1 on the second rectangle equals 2. Now let's go to the third rectangle. On the third rectangle, what is the height of this rectangle? Good, it's whatever the y value is here where x equals 3. So x is going to also equal 3. So for the third rectangle, we get f of 3 times again that delta x. Delta, so delta is actually, well, it's actually a Greek letter, but it's a triangle, right? And so delta in mathematics, hopefully you saw it in Cal 1 too, that delta gets used to denote change essentially. So the change, so the change from one x value to another. That's kind of what we're doing. And then for this fourth rectangle, what's my height here? Good, that's whatever f of 4 is, and my width is still delta x. So for the fourth rectangle, the area, so the area is going to be f of 1 times delta x, that's the first rectangle, f of 2 delta x, that's second, third, now fourth, and you add all these up and that gives you this area. Hmm. I think what I'm going to do really quick, so before we kind of keep going through the idea and the narrative here, is, so again, so this is how you calculate this. Notice that this is a sum of several different terms. So remember maybe from previous class that if we want, then we can write a sum using this big old Greek sigma symbol or E symbol, but sigma is a technical term there. And so we can kind of summarize what we're doing here. So every time for every rectangle, what we're doing is we're doing f of that particular x value. times delta x, which ends up staying the same every time. So the way we can write this is we can summarize this by saying, literally summarize this. We can say that the area is the sum of f of n, and n is going to equal 1. In this case, go all the way out to 4. So f of n, the sum of f of n times delta x. And actually, so I use n here because maybe in a algebra class they usually do that because they're thinking about a sequence or a series or a sequence. But I'm going to replace that with x actually. So let's call this so x from 1 to 4. But n is just emphasizing that in this case we're counting by whole numbers. So you would plug in a 1, then that gives you the first term, and you plug in a 2, and that would give you the second term, etc. All right. So when they were figuring this out, they wrote it this way, and then they quickly wrote it this way because this is obviously less to write. But when you see this, you need to kind of see this in your head. That's what we're really talking about there. Now we said that this is obviously an overshoot. So the question is then, how do I either undershoot or just how do I get closer to the real answer, right? These rectangles basically were just a bit too big, yeah, a bit too big, a bit too thick to kind of catch the real area here. So what do you think? How could we possibly sort of make this smaller and maybe catch the actual area? So maybe your thought is, so instead of that, so we were choosing basically to write rectangles basically with a delta x of 1. What if we did it at say a half? So what if this first rectangle again starts at, the height is f of 1, but this time I go out to, I make the delta x here a half instead of 1. So if I doing it this way, so what I want to do, just kind of bear with me. Well, okay, let's actually do it this way. So doing it this way, so what I want to do is I want to rewrite sort of the terms here with this new setup. So this time, my x values start at 1, but my delta x is actually half. So that means I would get the first rectangle now is definitely not as thick as the original first rectangle. My height is still f of 1, but now I'm multiplying by 1/2. That also means, so when I go to do the second rectangle, what x value am I using for the height? What x value do I plug in to get the height for the second rectangle? What's the height of the second rectangle? Good, so now what I'm plugging in, I'm getting a second rectangle that's like this, where this is 1/2, right? So now my second point is 1/2 or 3/2. But just to make it look like another line, we'll do that. So my first rectangle is still f of 1 times delta x. Now delta x is just smaller, it's a half. But my second rectangle now is f of, and I'm gonna write it kind of how we should write it, 3/2 times delta x. So again, notice a thinner rectangle. But notice that these rectangles, then the extra area that's above the curve is now smaller. And that's really the key here. So if you change the width, if you reduce the width on these rectangles, I'm still getting an area that's above the curve, but it is less above the curve. So then I would also get a rectangle here, but now it only goes out to 2.5. And I would get a rectangle starting at 2.5 that goes to 3. I would get a rectangle at 3 going out to 3.5. And I would get a rectangle from 3.5 to 4, 4 to 4.5, and 4.5 to 5. So notice now I have a lot more rectangles because each rectangle is a width of a half instead of 1. But again, take a look at the area that's above the curve. Well, how does it compare to the area that was above the curve when my delta x was 1? But it's a lot less. It's not just that it's less, it's actually kind of a lot less. So we cut, this is again going to be an overestimate of the area, but we cut our overestimate by a lot. So then the rectangles that I now have, my area calculation, or my area that I now have would be f of 1 times delta x, which is 1/2. But now it's going to be f of 3/2 times 1/2. And then we would have f of 2 times 1/2 for that third rectangle. And then f of 2.5. It's 5/2 times delta times 1/2. Plus, and you could keep going. You would have then f of 3 times delta x. Well, okay. Well, again, so now 3, this small rectangle is going to be f of 3 times 1/2. And then f of 3.5 times 1/2. Etc. So you're gonna, this is gonna be f of 3.5, 7/2 times 1/2. Or times 1/2. 5, 6, 7, plus now f of 9/2 times delta x. And this would be all 8 rectangles now. And this will give us our new area, our reduced area, still above the area of the curve, but our reduced area based off of the delta x being 1/2. Now again, we could rewrite all this, or we could represent all this in a much shorter, simpler way by saying, so every one of these terms is f of x times the delta x. Now just my x's are not 1, 2, 3, and 4. They're 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5. So this would be all the way up to 4.5. The only thing I don't like about this notation is, and even the other notation that they normally use in a calculus book, is that it still doesn't really tell you how they're counting, right? Like how they're getting from 1 to 4.5. So just since you've seen me do this, you kind of know that we're counting by halves. But so this is another general way to represent, or, this is a general way to represent this area. So basically, every time we do this calculation, we have f of whatever our, in this case, they call them left endpoints, or whatever our left value, x values are, times the delta x, and that gives you the area for each rectangle. You do it however many rectangles you have, and you add them all together. And so we can always re-summarize that using the sum symbol, because that's what this does. It says sum of a bunch of the same kind of types of terms, just with different numbers plugged in. So the sum of f of x times delta x, let's say from 1 to 4.5. Again, the huge thing is just by cutting the delta x to 1/2, we've got a much better approximation of that area. So again, classically for thousands of years, they were trying to basically monkey with this and figure out a way to make this fit maybe one of Euclid's equations, or just kind of make this sort of fit the area under the curve. Now, you might kind of see, and this wasn't, you might see a problem with continuing to do this, or kind of this approach. This wasn't a problem that other people didn't see. So again, they've been working on this for thousands of years, not because they didn't see the problem, but because they were trying to figure out some way out of the problem, right? So, anyways, so the problem here is that, again, this is an overestimate, and this is a closer overestimate but it looks like I'm always gonna get an overestimate, right? So let's talk next steps. So here we cut the delta x to 1/2. We could keep doing this. So we could cut the delta x to 1/4. Or even you could do something odd like 1/3. Or I don't know, 2/5 or whatever. But you could cut the delta x down. And if you cut the delta x down, you're gonna have more rectangles. And the numbers at the left ends of those rectangles are gonna be different. But you're still gonna end up with the same setup overall, f of x times delta x from 1 to wherever that leftmost or that last x number is. But let me kind of ask y'all, so if I cut this delta x down farther, what do you think is going to happen to this area, this approximation? Or good, it'll get smaller, but it's still going to be an overestimation. Also, what's going to happen to, so we're always starting at 1, first time we ended at 4, now we're in at 4.5. So if I keep cutting this down, okay, so if I keep cutting the delta x down, what's going to happen to this number? So what's that last x value going to be that we use for f of x? It's going to be kind of closer and closer to 5, right? So cut it down to 1/4, then the last one's going to be 4 3/4. If we cut it down to thirds, that last one will be 4 2/3, right? But it'll keep getting closer to 5. So we can keep playing this game, and they did this for thousands of years. We can keep playing this game. We can make smaller delta x's, but we're never going to get the exact area under the curve. We're going to get closer and closer, but never get the exact area. So what Newton and Leibniz did, though, is their kind of thought process was, well, now that we know limits work, now that we know this, so if you think about it, this is the limiting process. This is, you get one area calculation from when the delta x is 1, and then you get a second area calculation when the delta x is 1/2, and you get a third area calculation when it's 1/4, and then an 1/8, and then a 1/16. And like you guys are telling me, like you're kind of seeing, that area would be, and start with one number when the delta x is 1, and then it would be smaller when it's 1/2, and the area number would be smaller when it's 1/4 and a 1/16. So you have sort of a decreasing set of numbers. And just make sure. Basically, what Newton and Leibniz proved is that as long as this curve is continuous, that limiting process, or that sequence of numbers, has a limit. So they basically, the way they thought about this is, well, if we keep making the delta x smaller, what happens? So the question is, what happens as the limit for delta x goes to 0? Let's write it. What happens as the limit of delta x goes to 0? So if I take this width and I take it further and further down as a sequence all the way to 0, we said that right now we can see physically, and we can calculate this if we wanted to, that our area is getting smaller and smaller, so getting closer and closer to the area under the curve. So if I take delta x, the limit of this calculation is delta x goes to 0. What do you think you would get? Good, you would get the area under the curve. And so basically Newton and Leibniz just proved that. They proved that no matter how you split up these x's too, so these x's, the way we've been using the x numbers is, we started from 1, we use delta x as our counter. So 1, 2, 3, 4, and then 1, 1.5, 2, 2.5. They actually proved in what's called the fundamental theorem of calculus. They proved, or as part of the fundamental theorem of calculus, what they proved is that these x's don't even have to be evenly spaced. So you could make one big fat rectangle here, and then smaller ones here, bigger one here. But basically, the limit as delta x goes to 0, and the limit is, I won't say that part, but the limit is delta x goes to 0, no matter what x's you're picking here. As long as you take that delta x and basically shrink it down to 0, what Newton and Leibniz proved is that you actually get the area under the curve. So the limit as delta x approaches 0 for this calculation. And so basically also as this goes to, in this case, 5, right? Because that's the end of our area. So as the number up here goes to 5, yeah, let me write it that way. So what they proved is that the area calculation done exactly like we're doing it, starting at x equals 1 and let's say going to n. So the limit, sorry guys, just cheat. The limit as n approaches 5, f of n. Wow, sorry. Let's just make that. Let's just make that. I'll call this I. Like we usually do that as the initial point. Call that x. The limit as x approaches 5. For f of x times delta x, where we're taking delta x, the limit of that as it approaches 0. So as the width of these approach 0, and as you therefore push your x values out to 5, this equals the area under the curve. This is what they proved. So, I don't want to make this too complicated or too like verbally too weird and complicated by trying to say all the stuff that the theory says. But I do, so instead I just want to summarize. Basically what they're saying is, let's forget about, choosing x's in a different way. Just, as long this diagram, the limit is delta x approaches 0. So you take the width of those rectangles down to 0 is the area under the curve. Because at that point, you literally just have a stick under the curve. So if you think about it visually, you can imagine it. If the delta x goes to 0, then every rectangle is essentially a line that's right under the curve. And if you sum all of the lines up that sit under the curve, you have the area under the curve. So even visually, even from a geometry perspective, taking the limit as delta x approaches 0 kind of like it makes sense. It does what we need it to do. We need these rectangles not to have width. We need them to just be straight lines under the curve. So again, so Newton and Leibniz basically, because they proved that limits work and because they could algebraically prove that this limiting process, so what they had to do is prove that this limiting process has a limit. Then they were able to prove that indeed we can find the area under the curve. That's it, making these rectangles infinitely thin is what we're doing. Once you make them infinitely thin, they are just lines under the curve and you add them up and you get the area. Now the big thing about the fundamental theorem of calculus, so like I said, so I'm sort of introducing this calculation here, this f of x times x, and it makes sense for the diagram, but I'm introducing this symbol. The big thing about then what Newton and Leibniz did, so they proved that this works, and then what they proved, and this is the fundamental theorem of calculus, is that this calculation that you just did is actually just the integral of f of x. So what they proved in the fundamental theorem of calculus, a good way to look at this, is that by taking the limit as delta x approaches 0, so making the width of those rectangles get progressively smaller to 0, what you do is you transform this into an integral. So a sum of infinitely small rectangles is actually an integral. So this becomes the integral from 1 to 5 of my f of x, which is 3 over x squared minus plus 1. So again, think about it. I'm literally now just replacing f of x with what it is. So that's f of x. And this delta x And you've seen that before, that's just dx. So they literally proved, I mean, when I say proved, I'm sure that this was their instinct, they knew this had to be the answer, but you then have to theoretically prove it. And this is not a class where we teach you how to theoretically prove it. There's some work in the section, so again, if you want to read the section, that kind of gives you not the full proof, but enough of a proof that you can see kind of the sketch. But really, that's what they had to do. Is I'm sure this was the inkling, sort of the understanding that they had. They thought must have been the answer. But you have to be able to prove that this thing theoretically does actually become this thing, and that's what they did in the fundamental theorem of calculus. So they proved that when you're doing this infinite sum of infinitely small rectangles back to back, left to right, that is in fact just the integral. In fact, that's why the shape for the integral, the shape for the integral sign is an S. So if you think about it, sum. The sigma here, the sigma symbol, we always use for a sum. Sigma starts with an S, so there's the word sum. That's what an integral is. It's a sum. It's a sum of all of the straight lines, the infinitely small rectangles underneath the curve. Now, like I said to begin this lecture, it's also the inverse, the reverse, the opposite of a derivative. So that's really the amazing thing about the fundamental theorem of calculus is it sort of rolls and connects all these things together. It says, hey, you know how to do the derivative. Did you know that first of all, the derivative or the integral is the reverse derivative? But did you also know that if you want to find the area under the curve, it ends up that you're just going to use the integral, and that'll tell you the area under the curve. And it's also the reverse derivative. So hopefully you kind of see the transformation, the connection here. Like I said, because it's not a theoretical class, I don't have the time, especially because it's a 5-week class, I don't have the time to show you. But literally that's what we're saying here is basically, since we're making delta x progressively smaller, quite literally, this notation becomes this notation. Sum becomes the integral. Function, well, the function doesn't become a function, but then we can just write the function as it is. And the delta x becomes dx, and you have it. Now, the one difference between this and what we saw in the last videos, when we were doing integrals in the last videos, you didn't have limits on it, right? Because again, in the last video, we're thinking of the integral as just a reverse process. So the difference today is now, like I said, the motivation for this is I want to find the area under the curve. Now I can use, what I'm saying is I can use the integral, and as long as I, at the end, go ahead and plug in 1 and, so we'll kind of look at how we do this. But if I plug in 5 and 1 for my x values, then I can go find the area under this curve. So let's do that. So again, we had sort of all these faux calculations or approximations. What I'm saying is you make delta x infinitely small, you make these rectangles just lines, then you got the area under the curve. Again, Newton and Leibniz proved this connection and that it works, but now we need to actually do the thing. We need to calculate the area. So we've proven that this is how we do it. Now let's do it. So then how you do this is, first of all, you need to do the integral like we did in the last section. So you need to find the integral of 3 over x squared plus 1. So that's your first thing. And actually, I want you guys to take a second to do it. So again, just kind of a sneak way to get you to practice what I taught you in the last lecture. So go ahead and pause on your side. I'll pause on my side. First of all, figure out the integral of 3 over x squared plus 1. All right, let's see what you get. So let's just go over here with this. So 1 for integral from 1 to 5, 3 over x squared plus 1 dx. Good. All right, so we needed to take the integral of this. So again, this is x to the -2. So you go up in your power, that's -1. You divide by -1. So this first part, the integral of that is -3/x. And for the second part, the integral of that is x. But then again, we have to kind of talk about something, but that's your integral. So plus c. And then what we're going to do is we're going to evaluate this. So the idea, again, what the fundamental theorem calculus talks about is, again, they're going to say it's the antiderivative. That area is just going to be the area you get when you plug in 5 to this. And then subtract what you get for plugging in 1 for this. So basically, quite literally, the integral of this function becomes your way of calculating the area that this adds up to. And again, that's the huge connection that they made, that both Newton and Leibniz made in this fundamental theorem of calculus. So the integral actually tells you the area. So you do the what do you call it, the integral like we did in the last section, and now what we do is we plug it in. So we'll start with we plug in 5. So when I plug in 5, I'll get -3/5 plus 5. And then whatever that is, I'm going to subtract what I get when I plug in 1 for this, which is what, -3 plus 1. And once I work this calculation out, voila, I have the area. So let's work that out really quick. This is, let's see, 5 is 25/5, so this is 22/5 minus, and then this is really -3 plus 1 is -2, but then minus a negative makes it plus. So what this ends up being is 32/5. But again, a little bit like I was talking about in the last lecture, you have to make sure, please don't use decimals. Again, and here the decimal would be exact, but most decimals are not. So I want exact calculations. I want fractions. So 22/5 plus 2. 2 is another 10/5. So that's 32/5. So the exact area under the curve here, going back to our original, the exact area under the curve is actually 32/5, whatever unit we're talking about. So if we're talking about, ounces of paint or whatever to cover that, so paint to cover this, or a piece of sheet metal to fit right under that, right, or to basically take up the space there, it would be 32/5, whatever, square inches, square meters, square centimeters, etc. But it would be exactly 32/5. So again, this is what Newton and Leibniz figured out. They figured out that the integral actually tells us the area under the curve. So that same setup we saw in the last video, not only does it give us the derivative in reverse, but just having the function in dx actually is the calculation for your area. That's how we set up the calculation for area and all of our little, our couple little examples there. Good. So that would be the area under the curve, 32. All right, so let's do this. Let's do this for a couple more of these. Basically, so this section is just about, now that you see that connection, like if you have the skills, you can take the integrals. So let's go find the area under the curve. Just let me erase this for a second. Works and buttons. All right. Actually do the like the jump in and area under curves. So for this first one, I will need some pictures, and I'll take advantage of the pictures that we already have. So let's turn that on and bring this up. Right. So good. So you guys should be able to see some of the exercises in the book here. Let's look at. So we're going to find the area, the region under the curve, and so we have these problems. So, let's see, we just did that. Let's actually. I guess let's do something like 35 to begin with. So 35, our function is x minus x squared. So you see kind of x minus x squared as you expect, this parabola kind of facing upside down. And notice they've naturally given us kind of the cutoff here. We're evaluating this from 0 to 1. So we want the integral from 0 to 1 of x minus x squared dx. So you take the function, you multiply by dx, again, that gives us the area. And you can see the bounds on this pretty naturally. So we're going to evaluate this from 0 to 1. And we go. So easy enough. First of all, what is the integral of x? That's going to be x squared over 2. And then we have negative x squared. When you integrate that, what do you get? That's going to be negative x cubed over 3. Then we're going to evaluate this from 0 to 1. You're going to plug in 1, calculate that, plug in 0, calculate that, and subtract. So I'll actually give you guys a second to do that. So pause on your side, I'll pause on my side. Go ahead and work that calculation. All right, let's see what you're getting. So when you plug in 1, that's going to be basically, so you're going to get 1/2 minus 1/3 for that part. Then you're going to subtract. When you plug in 0, the nice thing is you just get 0, right? So that's incredibly helpful. So what we end up here, make sure you guys can still see this. Sorry, this is going to create a little infinite hallway, so let me move this over. So maybe like that. That's going to be 1/6. So we now know the area the area in this little cone area defined by a nice little parabola right above the x-axis from 0 to 1 is in fact 1/6. Good. So again, this becomes now our tool to find the area under the curve. Let me give you all one to practice with just from your own play. So I'll have you guys take a second and work 38 there. So erase this for now. So go ahead and pause on your side so you have that picture. This function is x plus sine of x. Go ahead and pause on your side and then work that. See if you can get the area under. So notice here again, they give us the curve. And again, by the visual, they naturally give you the values. So from 0 to pi. All right, so pause on your side, I'll pause on my side. Go ahead and work that. All right. So let's write out the integral we need here. So we need to take the integral from 0 to pi of x plus sine x dx. Good. So what did you guys get when you integrated the x? Good. That should be x squared over 2. And what did you get when you integrated sine x? We got to think about those derivatives of sine, starting with sine, it goes around in a circle. So for the integral, you're going backwards. The integral of sine x would be negative cosine x. We're going to evaluate this from 0 to pi. So let's start plugging that in. Especially, this is a good problem to do. Don't always assume that 0 gives you 0. Kind of like on that last problem, when we plugged in 0, we got 0. We said it was nice, and it was. But 0 doesn't always give you 0, depending on the function that we're plugging it into. So for instance, here, when we plug in pi, so the first, and another thing to note, when we plug in pi, we get pi squared over 2. Again, I want exact answers in this class, or we want exact answers. And so we actually, you don't want to multiply that out, approximate, round to some decimal. You've got to leave it like this, pi squared over 2. So it looks funky, but that is the exact value. So let's call it that, be comfortable with that, view it as that. So pi squared over 2 minus, now what is cosine of pi? The cosine of pi, if you think about the unit circle, is actually -1. Cosine is your x out of that unit circle. So minus 1 is actually +1. So this whole first part is going to be pi squared over 2 plus 1. Then I'm going to subtract whatever I get when I plug in 0. Now when you plug in 0 for x squared over 2, good, that gives you 0. So that part's nice. You plug in 0 for cosine. What's cosine of 0? Good, that's actually 1. So you get minus a -1, or really +1. So overall then, the answer for this is pi squared over 2 plus 1 plus 1, so +2. That is the area under that curve. So some of these problems where they actually find the area, they're gonna. I'm just trying to figure out how I'm gonna grade these sort of topic later on in the lecture. Good. So some of them are going to give you pictures. Some of them, though, like see these problems down here, they're going to give you the setup for it, but they won't give you pictures. They're essentially going to give you this, but in words and equations rather than a picture. So, for instance, which one do I want to play with? Let's play with. Maybe play with 41 here. What I'm going to do here, since there's not a lot of room on these, well, yeah, good. Yeah, I guess I might as well. Let me erase this, give ourselves some room to work. Let's look at 41 here. Let me check again. I should be able to. Honestly, because it's so small on the screen, what I'm going to do. Let me go ahead and write this out on the board because it's just not going to be easy to see that. So make sure. So we're finding the area, and the function here is 1 plus the cube root of x. And then they tell you all this extra information. This extra information are your boundaries. So they kind of tell you, well, we'll see. We'll kind of get a thumbnail graph of this going, but we'll put these, on those graphs that we just did. They showed you the function. They also gave you sort of some definition. Where was the bottom, which was usually the x-axis? Where was the left? Where was the right? So that's essentially what they're doing here. They're going to tell you x equals 0, one of my boundaries, as well as x equals 8, as well as y equals 0. If they give you something like this problem, just visually it was very nice. You saw the region you were trying to find the area of, right? So the problem here is they forego that and just give you the information, like I said, in terms of equations. So since the picture was so nice, what you should do with this problem, what you kind of really have to do with this problem is, again, you need to get a picture. You need to get a picture of what's going on, so that just like the last couple problems, you can easily just write out the unit. So let's do that. This is actually something, not just for a problem like this, you're going to see this as one as we go through this course a lot, that calculus, surprisingly, is very visual. But if you think back to what I was talking about earlier in the lecture, that actually makes sense, because calculus was really, it was again, mathematics used to one, solve two ancient problems. What do you call it? The slope of a line, or slope on a curve, and the area under a curve. Those are geometry, those are visual things. So the genesis of calculus is visual. So naturally then it should rely a lot on your visual senses, and you should rely a lot on your visual tools to figure out calculus. But two, you're just gonna see it just makes it a ton easier if you can visualize this. So that's what we're gonna do. So the first thing is, let's visualize this, let's try to get a graph going, so that like the last problems, we can just kind of see what we're looking for and write the integral on work. So for that, you're gonna need to rely on, so from here, let me go ahead and turn this off. And so you're gonna have to rely on what you know again from previous classes. So for instance, so we need the graph of 1 plus the cube root of x, or we need at least a thumbnail sketch of that graph. So again, you guys took college algebra, or you passed college algebra at some point. You not only you should know, you know what this graph looks like. So the cube root of x looks like an kind of funky S on its side. So the cube root of x, let's kind of take a couple transformations. Cube root of x normally looks roughly like this. And then what is this plus 1 doing to that graph? Good. So it's going to move the whole graph up 1, which means in particular, so it moves the whole graph up 1, but especially it moves this little x-intercept here at 0, 0 up to 1. So as a rough draft, this graph it's going to look something roughly, so it's going to hit up at 1. Just if you remember some of the points for this graph, that also means actually that it's going to hit back here at -1 as an x-intercept. So this thing is going to, this thing is going to kind of come back like this. And why I spug it. Like I said, this is a sketch of the graph. It's not really a completely accurate graph, but I do want this to look like it should. All right. We're gonna point there, we're gonna point there. And we're gonna point here. So this graph will look roughly about like this. Let's look at the other, the boundaries they give us. So x equals 0. What is that graph? What does that do? So remember, your x equals and y equals are actually, so the x equals is a vertical line, y equals is a horizontal line. So we're gonna have a boundary here. And we have a boundary here. So notice that kind of caps off the corner here. Then we also have a boundary at x equals 8. So basically we want to go out to 8. So this graph naturally kind of, so it's under this 1 plus x cube root of x curve. Naturally from, so what's my x value over here that it stops? That's 0. And what's my x value over here that it stops? That's 8. So this is the other reason you really need the picture is honestly, you're not necessarily always going to be able to see those boundaries just from the numbers here. Well, at least in this one you can. But by having this picture, you can see clearly, once you see all the lines crossing, you can see clearly the part or the portion of the graph you're finding the area of, and more specifically your left and your right end here. So this tells me again, my left x value is 0, I'm going from 0 to 8. This tells me that I need to find the integral from 0 to 8 of this 1 plus cube root of x dx. And then that's your test. So we dealt with some square roots and cube roots on the last lecture too. That's kind of your test. Can you integrate? And let's see if you can. So go ahead and pause on your side. I'll pause on my side. Let's figure it out. Let's see if we can get it. So when you're this again, like we talked about last time, realize that cube root of x really means x to the 1/3. So I'm actually so I'm trying to do from 0 to 8 integral of 1 plus x to the 1/3. Because once we see it that way, we realize that it's a power function, and we can kind of do our normal integration with power functions. So the integral of this is going to end up being x, 1 goes to x to the 1/3, you add 1, which is 4/3, and divide by that, so you get x plus 3/4, x to the 4/3. And we're going to evaluate that from 0 to 8. So plugging in 8, we get 8, obviously there. So the kicker is just doing this 8 to the 4/3. And again, you can run this in your calculator, and if you are, that's fine. That's what the tool is there for. When I look at this, I realize that the 30 on the bottom is a cube root, 4 on the top is a power. So I'm doing the cube root of 8. And what's the cube root of 8? That's 2. And then 2 to the 4th power is 16. So just kind of working that out. And then we're doing 16 times 3/4. So basically that first part ends up being, so 16 times 3/4, the 16 and the 4 cancel, and so you end up with 3 times 4. So this first part, when you plug in an 8, you end up with 8 plus 12. And when you plug in a 0, 0 is 0, and 0 to the 4/3 power, say 0 to any power, but yeah, I mean, this cube root is 0, 0, 0 to the 4th power is 0. 0 times 3/4 is 0. So this is just straight 0 out of all this. So what we end up getting, the area of this is 20. So the area of this funky looking little area is 20. If you printed a metal part on this and you painted it evenly, exactly, it would be 20 square units of whatever you're painting. And whatever the original dimensions were, square inches, square centimeters, whatever. Good. So specifically exactly 20. Now, I want to look at an example. I'm actually going to modify one of their problems in the book, but I want to look at an example. So every problem we've seen every area that we've done, so far in this lecture, I've noticed that when I set up the boundaries and everything, it was set up so the curve naturally was over the x-axis. So I've been finding the area under the curve and between the curve and the x-axis. So, what about, let's look at the following case. So this is my modification of 44 solid. 44 solid. So the curve that we're looking at here should be e to the x minus 2. Cut off by x equals 0, so my boundaries are x equals 0, y equals 0, and x equals 2. And I want to find the area under the curve, so that's okay. The instructions here are really find the area. Now, the first thing I want to do is I want to sketch this region for you because there's something that, again, without the picture, you just wouldn't just run this. So, graphing this. E to the x normally looks like this, but -2 means I'm going to bring it down to. Normally, it has a no x-intercept and it has a y-intercept of 1. Bringing it down to. No, actually, I may have to change this right boundary so I can sort of make this point. But let me. In fact, give me a second. Oh yeah, yeah. So by bringing it down to what I'm actually doing is I'm bringing that y-intercept down to -1. So maybe let's call that -1. So this starts here. And then at 1, let's see, this is e -2, which is still a little below 0. But then at 2, this is e squared. Well, no, hold on. I'm thinking it should be a little above 2. Actually, a decent bit above 2. Right, so natural number is like 2.78 roughly. So at 1, it's roughly there. At 2, it's actually a good bit up here. So it's kind of cross me. But basically, e to the x -2 looks roughly like this. It's going to have actually a horizontal asymptote at 2. The boundaries that they give you, so they give you x equals 0. Take this horizontal asymptote helps with just focus on it. They give you a boundary there. They give you a boundary at y equals 0, which is the x-axis. And then they give you a boundary at again 2. Roughly here. So what I want you to notice if you kind of look at, so I guess well, actually, don't just notice. So the question then is, how would you describe the little area, the pieces that we just defined, that we're finding the area? Good. And notice that you get this little area here. All true. But my boundaries go all the way back to an x value of 0, so I actually also get this little area here. So if they're asking me to find the area here, I gotta find actually the area of 2 different parts. This little bit and this little bit. Now let's think about that process or the explanation I gave you guys for the integral and how it relates to area. The example we did had a little area above the x-axis, right? So my f of x values, my height of the rectangles were all positive. Notice though, so if we just do the integral of this, your f of x values between here and 0, are they positive or are they negative? Good, they're negative. So if you take the integral through all the way from 0 to 2, the problem that you're going to run into is the area you're going to figure out here is actually negative because your f of x values are negative. So a negative f of x value times a positive dx value is going to give you negative. So literally this area, now this area in terms of geometry is actually positive. But based on the calculation that the integral is doing, where it's the f of x times dx or delta x, your f of x's are negative, so it's actually going to give you negative values here. So the problem is if we just take the integral as it is, so if we just do the integral from 0 to 2, e to the x -2, what it's going to do is it's going to add up all the negative areas here with all the positive areas here, and what you're going to get is not the actual area under the curve. You're going to get this positive area basically subtracting this area, because these are all going to be negative. So you're going to get something that's just not the area under the curve, right? So if they give you a problem like this and they want you to find the area, what you've got to do as a problem solver, so again, you have to have the pictures. You got to realize that part of this is the integral is going to read as negative area. And so once you realize that, what you got to do is we got to figure out where this x-intercept is so that we can find the area of this one little part and then the area of this second part, and then we're going to add those two together. Because by finding the area of that one little part, basically what we're doing is we're flipping it from negative to positive. So that then we can add it with the other part. And we're getting not only the true answer, but the thing that we want. Again, geometry says these are positive areas. There's no such thing as negative area. You're getting a negative in the calculation just because of how the calculation is structured. Your f of x values are negative, so they naturally give you negative answers for the area. Anyways, so that's what we got to do. So you have something like this to get, if the goal is to find the area under the curve, then what we're going to have to do is break this into two different integrals, one from here to here and one from here to here. And like I said, to do that, you need to know where here is. You need to know where that x-intercept is. So how could we figure out what that x-intercept is? And I'm asking that because, again, hopefully that lights a little light bulb in your head for you, or that, you know, it connects, as lights up a light bulb in your head, that if I'm asking you for the x-intercept, now you're not doing calculus, you're doing algebra. So first thing I'm gonna need to do is find this x-intercept really quick. Again, the only way you know that that happens, problem will not tell you that you need to do that. So you need to create the picture so that you can double check and make sure, you know, so you can see that you need to find that x-intercept to break this up into parts. And that's the only way you're gonna know that. But the x-intercept, I'm gonna do e to the x minus 2 equals 0. So you always find the x-intercept the same way, set your y value to 0, and then solve the equation you have. And the fun thing about calculus is this equation can be any type of equation. So this really is a, you know, when you have to do something like this, this is a have you mastered algebra? This is a summary of algebra. By the time you're done with algebra and pre-cal, you've seen a ton of different functions, and for all of them, you've set them equal to 0 and you've solved those equations. So now those are your memories and tools at your disposal. You should know how to solve any equation I put on the left here when it's set equal to 0. This one, easy enough. I add 2, so e to the x equals 2. I turn this into a logarithm. So this is the natural log of 2 equals x, and voila. So this little point here is actually the natural log of 2. So that means that I turn this integral into two different integrals. So I'm going to do an integral from 0 to the natural log of 2. E to the x minus 2. And that'll give me, the area of this area. So let me add something in here without trying to kind of work things too fast or add too many things at once. E to the x minus 2 is still, we know that e to the x minus 2, the y values, your f of x values are negative over here. So I will say the one thing that you're gonna have to remember and kind of you know, just as you're working this problem is this is still gonna give me negative values, which means this area, this calculation is gonna give you a negative area for calculation, which doesn't make any sense. The area is positive. So what that means is you need to adjust this calculation by basically, if you know you're gonna get a negative out of here and you want to turn it to positive, what would you do? Good. There's actually quite a few ways you could do this. The easiest way is just stick a negative in front of it. So if I stick a negative in front of it, I know whatever negative value I get out of this will automatically turn it positive, and then we have the area. We have the area of this little part. And then I'm going to add the area from the center. So that'll be from the natural log of 2 to an x value of 2. And this is with dx instead, sorry. So that's a dx, that's a dx. Good. So this gives me the area of the first little portion. Again, the negative just adjusts for the fact that we know this calculation is going to give us a negative, so this just flips it to positive. And then this will give me the area of the second little part, and then so once I add those two, I'll get the true area of this curve, between this curve and the x-axis. I just got the true area there. So then we need to work this. So I think for this one, give me a second so I'll just kind of talk us through this. Another reason I chose this problem, I knew this part would take some explanation, so taking the integral of e to the x is easy enough, right? So the integral here is going to be e to the x, so it's going to be negative e to the x minus 2x, and I'm going to evaluate that from 0 to natural log of 2. And then the second part is going to be plus, same thing again, e to the x minus 2x, but now what I'm going to do is I'm going to evaluate that from natural log of 2. And then we just got to go through the calculation. So let's start here. Natural log of 2, so we're going to get e to the natural log of 2 minus 2 natural log of 2. All these symbols. Sure. And then I'm subtracting whatever I did get when I plug in 0. 0 into 2x makes that go away, but e to the 0 is actually 1. And I'm just going to continue that calculation. E to the natural log of 2, e and natural log cancel each other out. So we're going to get 2 minus 2 natural log of 2. It's not squared, that's a 2. Minus 1. 2 minus 1 is a 1. And then, so what I'm going to do in this next step is 2 minus 1 is 1, and then I'm going to go ahead and distribute the negative through. So what we end up with is 2 natural log of 2 2 natural log of 2 minus 1 for that first part. For the second part, start with 2. So we get e squared minus 4 when I plug in 2. Then I'll plug in the natural log of 2, so it's going to be minus e to the natural log of 2 minus 2 natural log of 2. And then we can start simplifying from there. So e to the natural log of 2 is going to be a 2. So what I see here is we have e squared minus 4 minus 2 plus 2 natural log of 2. And minus 4 minus 2 is minus 6. So we end up with e squared minus 6 plus 2 natural log of 2. So let me see. I probably need to adjust the camera. Maybe not. No, looks like good. All right. So then I'll finally combine this all to get an area of, it looks like 4 natural log of 2 plus e squared minus 7. That would be our area under the curve there. Really quick, just as a matter of kind of driving home the point that I started with. Again, when you graph this out, you see that you have two portions, they're asked, two portions to, two parts to this graph between the graph and the x-axis that this kind of highlights here, that you're finding the area of. So again, if they ask you to find the area, you have to break this out into two parts. However, let's say you looked at this, you didn't realize it was two separate parts, and you just kind of integrated from 0 to 2, basically. You just took the original function, you integrated straight from 0 to 2. So let's say, well, let's say you just integrated from 0 to 2. This e to the x minus 2 dx. So you didn't bother to look, to look at the graph. You just saw it as one total thing, and you integrated from 0 to 2. Well, then our integration work is the same. So when you integrate this, you get e to the x minus 2x. And then we're going to evaluate that from 0 to 2. So what you get from there is what? E squared minus 4. Then we're going to subtract, plug in 0 for 2. Yeah, there's only one part that showed up on. That's a 0, but then e to the 0 is 1, so subtract 1. So notice what you get out of that. You get e squared minus 5. And if you want, you can throw these two results in a calculator. So I don't know, let me call this problem 44 direct. Or not direct, definite, and I'll tell you why in a second. So let's call this version of the problem 44 definite. Make sure you can still see all that good. So notice that even if you don't throw these in a calculator, just looking at them, they're obviously different values. So 4 natural log of 2 is for this part in the -7 to match the -5, this would have to be a 2, and it's not a 2. If it was a 2, it would come out in the simplifying. But even if you want to throw that in a calculator, you'll see it's not a 2. So these are not the same. And again, if you just wanted to throw both of these in a calculator, just check, you would see they're obviously not the same. So what happened? What happened, again, the idea here is what happened what happened here is because we didn't account for part of this curve being under the x-axis. Basically what happened is it took positive portion of the area and it just factored the negative portion of the area. It just did the total area from 0 to 2, but part from 0 to natural log of 2 was negative, counted as negative variance because your f of x, your e to the x minus 2 is negative between 0 and natural log of 2. So it actually subtracted those parts off instead of adding. So if they ask you to find the area, you've got to account for this, or else you do definitely get a different answer. It's not correct. It's not the area of the curve. However, another reason I want to bring this up is if they don't ask for the area, so if they ask instead for the definite integral, then what they're doing is they just want you to find the integral from left to right, from one boundary to the other. So basically, if they ask for the definite integral instead of area, they want the negatives counted with positives. They want you to just simply do the integral from left to right and get the, you could say it's the net area. It's not the total area, it's the net area. It's treating the portion of the x-axis like their negative area, and you're combining them with the positive parts. And so you're getting sort of the net area.
But they're not gonna call it net area. The idea is just basically, sometimes we don't care about it being the actual positive area between the x-axis and the curve. We just want what is the integral from here to here. They call that the definite integral. So let's look at let's look at a couple problems where they just want the definite integral and know that those you don't have to do this. You don't have to graph it, don't have to do any of that. Just get the integral and work it. So for instance, let's start with something like, I think it's 17 is the exercise I want to do first. No, not 17, 15. 15, they're asking for not area, they're asking for the definite integral. Or honestly, they'll just say find. And what they give you here is the integral from 1 to 4. That's right. So I have u minus 2 over the square root of u du. And so again, if they want definite integral, then I'm not worried about graphing this out and splitting it into parts. I just want, so this is really, honestly just more like the first section. I just want to know what is the integral now with those values, 1 to 4. So we're just going to integrate this. So it's, kind of, to summarize all my blathering, you're going to integrate this. So you're going to evaluate it from 1 to 4. And you're gonna call it good. You're gonna let the negatives be mixed with positives. So that'll be kind of your job is to integrate this. We saw some problems like this on the last video, but to remind you, so when you get something like this, notice that since we have one term in the denominator, I can split this into 2 pieces. This is u over the square root of u, and instead of square root of u, I'm going to write u to the 1/2 minus 2 over u to the 1/2 all du. And notice that there's some simplifying you can do there. We now have u to the first power over u to the 1/2. And what does that simplify to? Good. Just subtract your exponents. 1 minus 1/2 is 1/2. So we're really doing the integral from 1 to 4 of u to the 1/2. And then here I don't have a u on top, but we know that if u to the 1/2 is on the bottom, how can I rewrite that exponent? Good. That's going to be u to the negative 1/2. Good. So just remember those little points algebraically, because now looking at this, this is much, when you saw this to begin with, this looks like a funky thing. And what do we do with a fraction? How do we deal with the fraction? How do we deal with the square root? But by rewriting this out as 2 fractions, because again, we could, and by writing the square roots as 1/2 powers, then in this case, this comes out to something pretty darn simple, and we can integrate it from there. So from here, you want to integrate and evaluate from 1 to 4, kind of like we're doing on the first couple problems. So I will give you guys a chance to do that. Go ahead and pause, work through that, and we'll come back and make sure you're getting the right thing. All right, see if you can. So u to the 1/2, take the power up 1 and then divide by that fraction. So up to 3/2 divided by that is 2/3. So what I see here is we have 2/3 u to the 3/2. And then negative 1/2. So here's the fun one, at least fun to me, because it's like at first you want to do something, basically want to do something with its negative 1/2. Maybe make it work with the negative here, but again, because it's a power function, the first thing you got to do is add 1 to it. So negative 1/2 plus 1 is 1/2.
And we're gonna divide by 1/2. Which means we really multiply by 2, so this is gonna be minus 4 u to the 1/2, and there's no extra things to do with the negatives there. And then we're gonna evaluate this from 1 to 4. So when I plug in the 4, so if I plug in 4 here, the square root of 4 is 2, and then what is 2 cubed? Good, that's 8, and 8 times 2/3 is 16/3, so that part is 16/3. Then when I plug in 4 here, the square root of 4 is 2. And 4 times 2 is 8, so this is minus 8. And then I'm going to subtract, plug in a 1. So when we plug in a 1, square root of 1 is 1, 1 cubed is 1, times 2/3 is 2/3. And then square root of 1 is 1, times 4 is 4, so that's minus 4. Then we can start to kind of combine, essentially in some ways what you're doing is combining like terms here. 16/3 minus 2/3 is 14/3. -8 minus, so basically -8 minus a minus is plus, so -8 plus 4 is minus 4. And 4 is 12/3, so we end up with 2/3 out of this. So the total, the definite integral, the integral from 1 to 4 of this function is 2/3. And other than that, in this section, all the problems are going to be like this. You're either doing a definite integral or you're finding the area, but again, the key connection is area under the curve is actually an integral. So the integral allows us to do that. But otherwise, just like the last section, make sure, again, in some sense, make sure you're brushing up or know all of your derivatives, because these integrals are just the inverses of those derivatives. So if anything, you'll see kind of these first 2 sections give you a chance to just brush up and get a lot of practice on those derivatives. All the derivatives that you learned in the first class in Cal 1, because these integrals are just the inverses of those. On the next lecture, we'll start looking at, so all of the functions that we're seeing here are functions that you can evaluate individually, easily just from your basic derivatives that you know, so derivatives of power functions, derivatives of trig functions, etc. In the next video, and sort of the next lecture, in the next section, which I think is 5.5. Yeah, I think it's 5.5. We're gonna start looking at some functions that no matter how you massage them algebraically, like we just did here, you're not going to end up with just simple functions that you can integrate. So then what do you do? So they're still integrals, they're still inverses of derivatives, but they're inverses of I'll save the reveal for next time. But we'll figure out how to do the integrals on things that don't end up just being simple derivative patterns that you saw from the previous class. I'll see you guys then.